We're gonna cover stress concentrations today, and so we're gonna build upon area stress functions that we had discussed previously. And stress concentrations are situations where you have a disruption in the geometry, or you have a material property discontinuity, or there's a situation where that disruption causes a stress riser. Um, and so those locations tend to be areas where crack could initiate, and we have to pay close attention to those. Again, to summarize the equations of elasticity, we have three equations here. These are the equations of equilibrium. We have the six strain deflection relationships, and then we have the six stress strain relationships. 15 unknowns, 15 equations, very hard to solve for very general problems, but we can solve it approximately or exactly for specific cases, and that's very advantageous in design. We also have boundary conditions where tractions are applied a part of the surface, and then we have boundary conditions where you may have a fixed boundary, and with the loads applies in the fixed boundary, that's going to help us understand, along with the 15 equations and 15 unknowns, what are the stress states that are occurring within the body and whether the structure could fail catastrophically. Further, I would like to then talk about the connectivity between the different areas that we're talking about, right? So you have the external loads applied, and we also have internal loads that develop due to the external loads. And so those internal loads are going to cause stresses, and the stresses can be then used to calculate strains through the material law. And then from the strains, we can calculate deflections by integrating the strain equations. And those displacements can then be used to determine what the deformation of the system is. The strains can be used to predict failure as well. And then the stresses can also be used to predict failure as well. And so, um, a stress gradient can occur in a small localized area of a structure, and this high stress is referred to as a stress concentration. Typically, it's caused by a geometric factor, like I said before, say a hole in a plate, or material discontinuity, like a bonded joint, where you have two metals connected by a bond. And typically, you can also have these stress concentrations at contact locations. It can occur near changes in geometry of a loaded structure. The flow stress is usually going to then be interfered by these discontinuities, causing a high stress gradient. You also see these plates in tension or bending with holes, notches. Those are just simple examples that involve stresses. You also see situations like that with shafts that are under tension, bending, torsion, which may contain holes, notches, keyways, and so forth. And I'll provide some examples later on with closed form solutions that have been developed for the design process. So you don't have to solve these 15 equations and 15 unknowns. This is very hard to solve. So people have developed closed form solutions to make your life easier in the design process. So today's lecture is semi-practical. I'm going to be covering some theory behind stuff, but then I'm going to cover how you can use some of these equations in the design. Here's an example of an airplane which had square windows, and the square windows had a situation where the crack will initiate at these corners. Because that corner, when it was subjected to this far field stress, was such that the flow stress was disturbed by the square window. You can note that in today's windows in the aircraft, they're not square, they're elliptical, because this corner has a higher stress concentration factor by quite a bit compared to elliptical design. Other examples of stress concentrations are shafts with keyways, as you can see here in B. gear teeth in A, and I've seen cracks initiate from locations like this, by the way, in real life. Bolt threads can actually start cracking at these locations. Shaft shoulder, and then riveted or bolted joints, and then welded joints like this. So a hole in this case is causing a disturbance in the load path. You can think of this as traffic, right? So if all the lanes are open, the traffic moves fairly well. But if you put a disturbance, or in the LA, Los Angeles, somebody can drop a sofa. I mean, I've seen sofas and mattresses. You put stuff like that, then the traffic slows down, but the intensity of the traffic increases. And so very similarly, you can think of stresses as traffic, where you have higher traffic when you have these kind of disturbances in the field. And so anytime you have the disturbance in the load path, you find yourself with these high stress concentrations. And the goal of today's lecture is to cover the kinds of stress concentrations you can have and how you could estimate those. But before I get started, a lot of these problems can be solved using polar coordinate systems. So this is more of a summary of something we have covered earlier. And what I'm showing here are the equilibrium equations in polar coordinate systems, which is quite beneficial in using this coordinate system, given that we're going to look at holes and things that can cause stress concentrations that look like a hole. Strain deflection relationships as well in the polar coordinate system. And then we have the plane stress strain stress relationships, but we also have the plane strain stress relationship, which is the relationship that connects the stresses and strain. To remind you one more time, we have the equilibrium equations, the strain deflection relationships, the plane stress equations, and the plane strain equations. You can either have plane stress or plane strain, but not both. You have to make an assumption of which one makes the most sense for you. For plane stress, the body tends to be thin, and so you cannot develop too much transverse stress. In this case, the z direction is the transverse stress. Anything related to the z direction. In plane strain, you're looking at fairly long bodies of material that could have constrained ends.